Okay, before we start 2.3, we're just going to look at the exercises that were there at the end of the last section, which was to check whether y is a function of x. We have x squared plus y cubed is equal to 1. And remember that I hinted that if you have an odd power of y, this probably, at least at this stage, probably this is a function. So what we want to do is we want to solve. We can't do this by plugging in numbers, okay? So you have to do it generally. So the idea here is to solve for y. So we have y cubed is 1 minus x squared. Now to get out of the cube, you have to put both sides to the 1/3 power, or take the cube root of both sides, whichever way you want to think about it. So y cubed to the 1/3 power is equal to 1 minus x squared to the 1/3 power. And that's a legal operation here, to put both sides to an exponent. And that gives you that y is actually the cube root of 1 minus x squared. And this is the nice thing about the cube root, is you can take the cube root of any number. So we can now say this is a function of x, which is the cube root of 1 minus x squared. And just FYI again, the domain of this function, it's all real numbers. You can plug in anything you like, because you can take the cube root of any real number and it'll be a real number as well. Okay, so that was the first part. The second part was we were given 2x to the 4th plus y squared x is equal to x minus 1. And so here it turns out that, excuse me, it's not a function. So let's plug in anything. Let's just say we plug in x equals 1. What would happen? Let's see, we would get 2 plus y squared is equal to 0. Well, so this number is not a great number. And the reason being is because we get y squared is negative 2, and that's not that's not good, because we can't take the square root of a negative number. So that particular number doesn't work out, but we haven't lost all hope. Let's go the other direction. Let's try some large negative numbers here. Let's try negative, say, 2. What would happen? Well, we would have 2 times negative 2 to the 4th minus 2y squared is equal to minus 3. So we would have 2 to the 4th is 16 times 2 is 32. So we have 32 minus 2y squared is equal to minus 3. Minus 2y squared is equal to minus 35, bringing in the 32 over there. So y squared is positive 35 over 2. And now we're in good shape, because now y is plus or minus the square root of 35 over 2. So we started with this single input of x equals minus 2, and we got multiple outputs. So hence, it's not a function. Y is not a function of x. Okay, so those were the exercises from the previous video. We're going to jump now to 2.3. And the primary thing I want you to get out of this is the net change concept. I'll also talk a little bit about what they call increasing and decreasing, but that's really a topic that is meant primarily for if and when you decide to take calculus. So I'm going to talk a little bit about that, but primarily I'm just going to talk about this concept of net change. So I'll do this by an example. So let's say you have a person. So there's a person. who, let's say you start the time right now, and the person is standing on the ground somewhere, and we'll label the ground as, say, the x-axis, and you're starting at x equals 0 is right here. At time 0, you're right here, right? And the time starts. And the person initially is here. Then at time, say after 1 second, you move forward to this spot. So after 1 second, you've moved over 1 unit. And let's just say after time 1, by the time you're at 2 seconds, you're back. So let's say by the time you're at time 2, you're back at the 0 point where you started. So what we would say then is the net change of x on the time interval t equals 0 to t equals 2, the net change, the net distance, well, it's where were you here? Well, you were here at 0. You started here at 0. After 2 seconds, you ended at 0. So the net distance traveled is 0. Okay, the net change or the net distance traveled is 0. Okay, so so this is kind of the intuition of net change. It's not really a hard definition, but I wanted to give an example that's sort of practical. Let's do this with a function. So let's just define. So define now a little bit more formally. So given a function, let's call it f of t. So thinking of it as happening in time. And f of t on some interval, some time interval a to b. Well, then the net change of f of t on this interval a to b is f of b minus f of a. And you can think of it exactly like this. If you wanted to think of, instead of x, this is a function where the function tells you where you are in time. The net change is simply where are you at the end of the day in relation to where you started with. That's the net change. So this is it's a fairly straightforward example or straightforward definition. Nothing too complicated. So let's do an example. Let's say f of t is negative t squared plus 1. And we want to find the net change on the interval, say, -1 to 3. Well, this is our a, this is our b. It's simply f of 3 minus f of -1. And that's -9 plus 1 minus, if you plug in -1, you get -1 squared plus 1. So you have -8 here minus, this is -1 squared is 1, and then times another one, so you get -1 plus 1. So this is simply -8 overall. So the net change here is -8. What else do we need to do here? There's not a lot more to this net change concept. It can be applied practically, for example, if you're traveling or things like that, but there's not a lot more going on. What we're going to do is we're going to look into this concept of increasing and decreasing very briefly. And I'll do 2 examples, one just with a graph and one back with the same function. So let's say you had something like this. So let's say this point was -5, -1. This point, sort of the top of this hill, was the point -3, 6. This point here at the bottom of the hill is, say, the point 2, 1. And then we end over here at, say, 7, 10. Okay? Now, you can imagine yourself traveling from, we always orient from left to right. So we're going this way. So you can imagine yourself, say, climbing this hill, and you're going this way. Apologies for the poor drawing here. But essentially, you're going uphill here, right? So this is an uphill. This is a downhill. This is another uphill. And essentially, when you're traveling from left to right, whenever you're going uphill, we say the function. So this is of some function, f. So f is increasing when you're going uphill. I know this is a very non-mathy definition, but it's sufficient for now. And essentially, what do we say? Where is it increasing? We look at the x values. So the x value right here is -5. The x value right here is -3. So we say f is increasing. So f is increasing on the interval -5 to -3. And for reasons for which at this point I probably can't really explain, at least not that precisely, always keep these as open intervals. Okay, always keep open brackets. Always keep open brackets. So f is increasing here. F is decreasing on downhill locations, downhill regions. So we say f is decreasing, and we again use the x value. So this is the x value of 2. So f is decreasing on -3 to 2. And then f is increasing on 2 to 7. So this is the idea of increasing and decreasing. Simply, it's when you're going uphill and when you're going downhill. It's really all I want to say about increasing and decreasing. All I'm going to do now is leave you with a little exercise here, or maybe 2 exercises. So one. So for our function that we started with, for f of t is -t² plus 1, when is f increasing and decreasing? So this is part 1 of the exercise, and part 2 is for, say, g of t is equal to the square root of 2t plus 1. Find the net change on the interval, say 1, 2, 4. Let's make it 0 to 4. Okay. So that's it for now. And this pretty much actually concludes what I want to say about 2.3. There's not a lot that I want to say. There's more in the textbook, but I have decided to not include some material there. And we'll start the next video with these exercises.